Hey everyone, in this video I want to explore a few terms we hear over and over again when we talk about artificial intelligence, when we think about generative large language models. We have terms like RAG and semantic index and semantic search and vectors and embedding. So what do all these things mean? So my goal in this video is to walk through them and explain why they are so important. Now, if I take a step back and I completely ignore the idea of technology for a second, I can think of some interactions I have had in the last week. So there's me. Now, I am really the sum of the things I've learned over time. I've been trained on various books and information. So I have a set of capabilities in my brain based on how those neurons are connected to respond and perform certain functions. Now, I had a customer, and the customer asked a question. And the question was, hey, is my Azure environment resilient? Now, I have no access to their environment. I have no knowledge of their environment. So with my abilities that I have, I can't generate a response based on their question. Instead, I need some knowledge. Now, if the customer then says to me, hey, can you tell me if my environment is resilient? By the way, I can run queries. I have permissions against the Azure cloud, and I could send you the responses. Well, this now changes things. They're telling me a tool set they have, so I can say, well, here's a plan of the things I want you to do. They can then run those Azure Resource Graph queries. They get a set of responses, and now they can ask the question again, but they add the responses to those things that they gave me. Now, I can give them a response. I have not changed really what I've been trained on. I've not relearned their environment, but based on the request and based on information they gave me, well, I can take my existing knowledge and skill set and with the extra data, give them a response. Now, the same thing applies with the idea that also it's the same me. It's not a clone, it's just a different time. My boss, we'll make them kind of angry, devil. My boss asked me a question and it was, hey, can you give me a summary of the meeting? Well, I don't have the detail of that, but once again, my boss has access to, in this case, the Microsoft Graph, and they can put in a request for the transcript of the meeting, and then they can ask me, hey, can you summarize this for me? And here's the transcript, because they're too important to bother to read it themselves. And then again, based on the knowledge that I've been trained on, the skills I have, they ask me the question and provide the transcript, so they're giving me different data, well, I can go through it, and then I can very begrudgingly, but I can give them a response. So it's the same me. I've not changed my training in any way, but based on different information they had access to that they could pass to me as part of that question, it enabled me to do different things. So if we think about really what's happening in these scenarios, well, they are doing a retrieval of data that is augmenting my ability. So it's augmented the ability for me to generate content. Retrieval augmented generation. So that's RAG. That's all it is. It's the ability that as part of the prompt that I'm going to give a large language model, I go and fetch some other information that's relevant, that's going to augment its ability to generate a higher quality response. So information is being retrieved, that's going to enhance its capabilities. And that's really all it is. When we talk about RAG, it's just, hey, the model is trained on some data, but I want it to be able to respond based on a different set of data. And that's what this is all about. So let's actually talk about computers. That's probably a bit more useful when we really want to think about what's happening and why we take that approach with a large language model. So think about for a second how a large language model actually works. There's a huge amount of training. So the whole point is we have this training, and that training is based on huge amounts of data. It takes a huge amount of time, a huge amount of computational power, a huge amount of money. So all of that training goes in, and that's what creates this neural network. We go through many, many iterations. We create these hugely powerful models. And at the end of it, once it's finished all that training, we get our large language model. That's what enables it to be generative. And based on information we give it, it can then do inference, the ability to predict, well, what should come next, i.e. answer whatever we are giving. Now, a key point at this, once the model has been trained, it's essentially read-only. That model is now usable, but it doesn't change. It's hugely time-consuming and expensive to train that model. So we're not constantly retraining it every time I send an email. That's not what's happening. This large language model is now complete. And what's actually happening behind the scenes is if you think about, again, I work in the Microsoft space, so I'm going to focus just those for examples. If you then go and look at things like, well, hey, it has a copy of this large language model for services like Bing Copilot, for the Azure OpenAI services. When we think of things like Microsoft 365 Copilot. It creates different instances that live within the various regulatory and privacy requirements of those particular services. But they don't change the model. It is that same large language model. Which therefore, how does it do that job? If all it knows is what it's trained on, how is the Bing able to go and get information from the web? How does the Microsoft Copilot know about things in our documents, our email messages? How does the Security Copilot hook into those things? So obviously, we need the ability to get extra information into those. And I did a whole video on how large language models work, so I'll link to that up there if you're interested to that. So, okay, great. We have these large language models, and we know these various services do different things. And as the example of me, well, I can do different things based on, well, what additional information do you, the person asking me to do a task, have? And based on the prompt, the question you're giving me, it's my same brain, but I can do different things. And my ability to respond is, in a huge part, based on the quality of that additional information you give me. That whole garbage in, garbage out will apply here. If you don't give me good data, well, my response to you is going to be not very good. So we have the large language model. So how do I get it additional information? Well, you've guessed it already. Obviously, we're talking about that whole point of the RAG, that retrieval augmented generation. That's exactly what we're going to use here. This is the key point. Now, when we use these services, we don't actually often just talk directly to the large language model. What the solution is actually going to do is there's some orchestration engine. So we have an orchestration. Now, there are different solutions for this. Microsoft has a semantic kernel that enables us to perform a lot of this, but you'll hear the term grounding. And so what's happening here is we have a user, and that user makes some request in some context to depending on what tool they're in, what they're actually doing at this moment in time. Well, I need to get additional data before I send it to the large language model. Because if I just say, hey, summarize all the messages from my manager, it has no knowledge of that whatsoever. It has to get more information. Now remember, one of the things a large language model can do is it can help generate a plan. Just as it said to me, hey, I want you to tell me about my resiliency, I have access to Azure. I said, well, okay, run these commands for me and send me the responses. So sometimes this orchestration will actually use the large language model, telling it what it wants to do, and hey, here are the tools available to you, and then it will respond with the plan of the things it wants you to do. Because there is some knowledge. It could be the Microsoft Graph, it could be some database, whatever that is, the orchestration will then go run whatever the question it needs to do. It will get the data back and then send that with the prompt and whatever that data is to enable the large language model to respond with a quality response based on what the user asked, based on this additional information. That additional information, remember, was all about the retrieval augmented generation. This is what makes it powerful, that ability to go and get the knowledge and add that to the prompt. So now that large language model, it doesn't have to have been trained on your data. It's impractical to do, but as part of the prompt, I'm getting additional data to give to it so it can now, hey, do really good decisions. And it's those improvements in the grounding, it's those improvements in the ability to go and get the most relevant data is how we see these huge improvements in the types of responses these actually give. And this is why, again, Microsoft 365 Copilot, they're not creating a special version trained on your data. That's completely impractical. It's the same large language model that was originally trained up there, but you have access to certain data. The orchestration acts on your behalf to make queries against some knowledge set. The Microsoft Graph, security APIs, Azure, RESTful APIs, whatever that might be, whatever the context of what you're trying to do. So the large language model can perform different levels of help depending on, well, what tools it's told is available to it, what additional augmented retrieval is possible to help in its generation. Okay, so if RAG is the ability to go and get information to make my response better, then what's the big deal with all those other terms? Remember, we had all those other terms floating around. What do we have? So we talked about the idea of vectors. We had the idea of semantic, indexes. You'll hear about semantic search. You'll hear about embeddings. What's all that about? How do these terms play into the idea of this retrieval augmented generation? Why are they important at all? So if I think about this typical knowledge that we have here, very often that knowledge, well, that knowledge could be in the form of text. It could be a document, PDF file, something else, JSON, docx. It could be an image. It could be audio. There's a whole set of different formats that could be in. And if I just think about the English language, I use the word manager. Well, there's a whole bunch of synonyms for that. Manager, boss, leader, etc. And some words can mean different things depending on their context. Some things are similar. And so if I was just to use a traditional exact match or even a fuzzy search where a few characters could be different, we call this a lexical search. If this data was just stored in a regular database and I'm using natural language, there's a lot of flexibility. If I try to perform a traditional exact match search on the words, it's not going to work very well. When I'm in these natural language environments, those lexical searches which need the exact term or maybe a character or two out, it's just not going to function very well. I'm not going to get good responses, and it's not going to work when I have things like images and audio. It's going to break at that point. And so how do I solve that challenge? And especially if we think about with computers, they really prefer working with numbers anyway. So what we have to do is we have to take this and we need to run it through, we call it an embedding model. And what this embedding model is going to do is going to create this one-dimensional array of floating numbers over a huge number of dimensions. That means it has, with vector, we think of, hey, direction and magnitude, but it's going to have hundreds or thousands of numbers to represent the data. But it's not just going to represent the words. The whole point of this is going to represent the actual meaning. It's going to be an interpretation of the information. So that semantic meaning of the context, not just what was the actual basic input. And so this data, we're going to run it through an embedding model. Now, these embedding models have been specifically trained to perform this task. This is not the same model as the large language model. This is specifically trained to create vector representations of the input. Now, a very common one you'll see is Ada 002, and that's actually what I'm going to demo here. So the whole point of this is I'm going to send it my input, and there are versions that can work against text and documents. I can do it with images. Typically, then it's going to use image to understand what's in the image, the context of the image, and then apply it to the vector. Audio, the same videos. I can take all of these things, but the net result is it's going to spit out for each of those. It's going to create a vector representation. So this huge array of floating points, it's going to be much bigger than this, et cetera, et cetera. And then obviously it's going to store them. So I'm going to go and store that in something. I'll just draw this. And this is going to be my semantic index. So the whole key of this is going to store those values, and it has its own index specific to these vectors that it's generating, which is a science unto itself to actually create those indexes that's going to then enable us to quickly go and find things in there. And so for a bit of fun, to give you an idea. So I went in and I've created an instance of the Ada 002 model. And all I'm going to do is here, I'm going against my particular version I've created. And my input is, can you tell me about embedding models? Now, obviously, I could put in anything I want. Hey, tell me about pizza, blah, 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 blah. I'm going to run this, and I can convert the output, which is JSON, into some objects. So you can see that completed. If I then go and look at the embedding, the actual embedding, not one character, well, there's a lot of numbers. All of these floating points. How many is there? Well, it's 1536. It's always 1536 with the Ada 002 model. But we can see the whole point here is that, yeah, we got this embedding back, which is the vector representation of the meaning, the semantic meaning of my input. And then that would go and be stored and utilized in other places for how we're going to use this in the future. And that's really the whole point of this. The whole idea of these embedding models is whatever that input object is, the embedding model will then allow it to be described in this vector space. So now we have this number, this representation of it. Now, if it was a very large amount of data, it will chunk it up. It will break it into chunks to enable it to run through and be stored. Now, when you hear the term embedding and you hear the term vector, they're very often used interchangeably. I guess to be the most accurate, the embedding is the representation of the data in a structured way, whereas the vector is that numeric representation. But again, you're often going to hear them interchangeably. But the point is, now, these vectors represent the meaning, that semantic meaning of whatever the input was. So even if the words were different, it understands the meaning. So like inputs will have similar vectors. They're going to be on a, again, I can't visualize 15,036 dimensions. I can barely visualize 3. But you can imagine there's that vector that represents. And so there'll be similar vectors if that input is similar as well. It's probably easier to understand if I try and put this in 2 dimensions. That's basically as much as my brain's going to handle. So in 2 dimensions, if we think about it for a second, then I would have this idea of that idea of a boss, manager, a leader. They would all be grouped close together. If I had cat, kitten, and remember, it would work with pictures. So if I had a picture of a cat that was actually distinguishable as a cat, it could also have that as a vector, and so that would be close as well. So it's going to be able to merge these different things together. So now in those 2 dimensions, I can get the idea that things that had a like semantic meaning will be closer together. Their vectors will be closer together. If I think of having those 1,500 dimensions, think how richer those meanings can actually be. So my whole point is I'm building up my semantic index that has all of these vectors in it, which now makes it more retrievable by my solution. Now, as I showed there, I work in the Azure space. So this is Azure and the Azure AI Search, which was formerly known as Azure Cognitive Search. So that does the job of creating these embeddings, and it can get that from Blob, from Azure SQL Database, from Cosmos DB, Data Lake, etc. It handles cracking open the files. It could be a PDF or whatever, chunking it up, creating those vectors. And they're designed for the very fast retrieval and similarity search. That's really a key point. You'll also hear today about a number of database services are starting to hook into AI services like Azure Cosmos DB for MongoDB vCore, Azure Postgres SQL Database. They now have the ability to call into AI services to go and get those vector representations generated, and then they get sent back and they can store them, and then they can perform vector searches as well. So this is why you keep hearing about vector search and embeddings. It's key to the whole point of making these large language models work on your data. It's why if you want to do Microsoft 365 Copilot, it talks about having to have the semantic index enabled for your organization. Hey, your Microsoft Graph, it has to go and create these vectors for all of the data in it to make it function. Okay, so what does all this have to do, though, with actually doing something, actually using this? Well, remember, I have some question. I have something I want to be able to find against all this data. So now as the user, well, that user has a question, but the question goes into the same embedding model, which means the question now has a vector generated for it. So now the whole point is, oh, not that. So now the whole point is we do a semantic search. And that's the end result we really, really care about. the whole point of the semantic search is these systems have the ability to mathematically go and find the smallest angles between those vectors, i.e. the nearest neighbor. And I could maybe say, hey, I want the top 3 nearest neighbors returned to me. And so even if the original words were completely dissimilar, it doesn't care because it's based on the semantic meaning of what I typed in. So if my question here was based on the word chief, for example, I typed in chief, well, semantically, they'd still be close together. So it would be able to find responses that talked about boss or manager or leader or any of those things. So the net result would be, when I think of that retrieval augmented generation, I'm going to get the closest data. I'm going to get the highest quality, the nearest neighbor. And that's possible because of these embedding models that create the vectors that represent the semantic meaning of all my data, that then create one based on the semantic meaning of my question, find the closest nearest neighbors based on those vectors and a whole lot of really clever math. And so now the end result is I'm going to send the highest quality nearest neighbor data with my prompt to the large language model. So it's got the best input, the most relevant data. So it's going to give me the best output. That is the whole point of that. And this is why those concepts of vectors and embeddings and semantic index and semantic search is so important. Without that, I would not get quality results against the data that's going to enable it to do its job. That's why we focus on that so much. If I just did text-based queries, it would not work. Now, you will hear concepts like hybrid retrieval because, funnily enough, the semantic search is not great at exact matches. I'm trying to find this exact SKU, maybe a part number. Well, that's actually where an exact match, a lexical search, would give a better result. So what you're seeing in a lot of these solutions, the Azure AI search, is it will do a hybrid search. It will do the semantic search against the vectors, and it will do a lexical search against the exact words, and then it will fuse those together, and then it will run other algorithms on top of that to find the best possible results, which it then gives to the orchestrator, which then adds to the prompt and sends that in. And so there you go. I mean, that really is everything. That's a fairly high level, but that's why it's so important. The large language model is not retrained every time we send an email or anything else. That's impossible. The whole point is it doesn't need to be. We have the ability to add additional information that we retrieve from a system that will augment its ability to generate a quality response. And what enables us to retrieve that great information is we take all our information, we create a mathematical vector representation of it based on its meaning, its intent, that semantic meaning, through an embedding model that we store in this index that is designed for fast retrieval and to be able to do those searches for nearest neighbor, the closest, the smallest angle between them, that it can then give back to me, that we can add to the prompt, and we get great results. I hope that helped. I hope that was interesting. I thought this was really, really cool. As always, till next video, take care.